All right, hi everyone. Today we'll be talking about Coulomb's law and the electrostatic force that we can experience when we kind of build up static electricity and whatnot. So, in today's lab, what we'll need to begin with, just cut out a small square of aluminum foil. You'll need a ruler so that we can measure the distance between the object that we're going to charge up and the foil itself, and obviously an object to charge up to create that static force. So you can use like a comb to comb through your hair. Unfortunately, I don't have too much, but luckily you can use something like a balloon or whatnot. You can try and find things that can build up some static electricity. Usually the best things to really do that are going to be insulating objects, weirdly enough. So anything that's plastic, rubber, things of that nature will do the best to kind of build up that static electricity and hold it for a while we manipulate our object to undergo electrical force. All right, so here we have a few things a couple of things that we're going to be working with are a little piece of aluminum foil, a ruler that can measure in centimeters, and then something in order to build up that static electricity. For my case, it's going to be a rubber balloon. So just if I hear that, charging this up, and then hopefully with building up that static electricity, have to do a little bit more. And then we get some of the electrostatic force. So what we're trying to do is we're trying to get the object to essentially lift off the table and overcome its force from weight, so the force from gravity. And so we're going to try to measure that exact point in which that occurs. So if you have like an object such as a balloon, it's going to be a little bit more difficult to accomplish that, but hopefully, regardless, we can still do this even with the fact that the balloon is a little bit more clumsy to work with. So let's try and do that just to show it an example, and hopefully you'll be able to see if we charge this up. Our ruler kind of close by. Maybe we can get it somewhere around there. So if we look as close as we possibly can, maybe it's about 2 centimeters or so. Try your best guess at it, and then do it, about 5 times or so in total, so that you get a nice statistical average. I recommend just using the same square of aluminum foil. If the aluminum foil isn't quite being lifted very well, just kind of reduce the size of it so that its mass isn't so much. Another thing to help with trying to build up more static electricity, particularly like if you're using a balloon or a comb, the best conditions for static buildup are when it's cool and dry in the atmosphere. So this is why in the winter you oftentimes feel more of that static electricity building on yourself as you're moving about, because of that cold and dry environment. Whereas now during the summer, it's very humid and really hot. So if you're having some difficulties with trying to accomplish that, try and, to the best of your ability, make the environment a little bit less humid, so that that static electric buildup can occur. Alright, so I'm going to kind of switch gears right now from the demonstration to sort of the application of what we're trying to accomplish here. What we will attempt to do is estimate the amount of charge that we're actually building up on either our comb or in my case the balloon, and we'll try and do this by applying the same principles that we've learned before in regular mechanics, that we'll use free body diagrams to demonstrate that there's a force being created by the electrostatic attraction of the charges on our charged up object, and that there's a force from the weight itself in that sense. So here I've drawn the free body diagram of the aluminum foil, represented like this, and that our object in this particular example here, I drew a comb that's been, for the sake of argument, negatively charged, and that it is going to be some distance away from the foil, and what we're going to try and do is capture that particular moment when essentially F sub E, the electrostatic force, overcomes or just about equals the force of weight. All right. So the way that the electrostatic force works, particularly with aluminum foil, since aluminum foil is a metal, it is a conductor. And since it's neutrally charged, that means the charge in the entire aluminum foil is going to be evenly distributed throughout, with the same number of positive and negative charges, kind of just distributed randomly throughout and more or less evenly, making it electrically neutral. When we bring something like a charged comb near the aluminum foil, what will happen is that like charges will repel each other and unlike charges will be attracted to each other as well. So in my argument here, if the comb is negatively charged, the negative charges in the aluminum foil will be pushed away, and the positive charges will remain at the surface of the aluminum foil. The aluminum foil, even though that it is very thin, it does have a thickness, and this is something that will be important when determining the mass of our foil. Typical foils run about 16 microns in diameter. If you get heavy-duty aluminum foil, it's a little bit thicker, but they're very thin. And even in this case, what we'll do is we'll just kind of assume that more or less the positive charges act more strongly than the negative charges are repelling in this particular instance. And so the charges of these two objects will be dictated more or less by the positive charges on the surface of the aluminum foil and the negative charges in the comb itself. Right? So again, I drew the free body diagram here of the electrostatic force going upwards and the weight of it going downwards, since these are the only two forces acting. And what we want is the moment in which they become equal, or effectively once the foil starts to lift off of the flat surface you placed it on, say your table or whatever. All right. So this is just going to be an estimate of the charges that's built up on, say, our comb, or in my case, the balloon. So we'll use Coulomb's law here, which is stated as K Q1 times Q2 over R squared in the scalar version of Coulomb's law. K is just a proportionality constant equaling 9 times 10 to the 9 Newton meters squared per Coulomb squared. So basically makes the units cancel out here in order for us to get a unit of newtons as expected in the case for forces. And like always, weight is just mg, mass times acceleration. In this case, our acceleration is due to gravity, since that's how we define our weight. All right. In this case, what we're going to do is we're going to assume that the magnitudes of the two charges on our comb and at the surface of the aluminum foil are approximately equal. There's some arguments to say that they're not quite equal and all that sort of stuff, but for the sake of simplicity, and just as an estimate of the charges themselves, we'll just say that they're equal, and we'll just call it Q. Alright, so then we can rewrite Coulomb's law in this particular form where we have kq squared over r squared equaling the weight, and then we just do our little bit of algebra in order to solve for the charge based on this particular system, which gives us this particular relationship. And we'll take the positive root of this. Since we're just getting a magnitude of the charge, we don't really care too much whether it's negative or positive at this point. All right, and just as a reminder again, newtons are kilograms meters per second squared, so hopefully everything, when you do your unit analysis, everything works out in the end. All right, the one thing that you'll need to find out is the mass of the aluminum foil. I did provide the thickness, which will play an important role in determining what the volume of the foil is. Here I've given the volume of the foil itself as the thickness times the area of the foil itself. Once we find the volume, we can multiply it by the density of pure aluminum, and then we can just find the mass fairly easily in grams and convert that into kilograms so that we get the proper units out in the end. So all you would need to do is just measure the length and the width, or the length and the width of the aluminum foil, and then in centimeters, multiply it by the thickness. Use the density that's given here of 2.7 times, just 2.7 grams per cubic centimeter. Since we have everything converted into centimeters already, just leave the volume in cubic centimeters and multiply that, and that will give you the mass in grams. Convert from grams to kilograms in order to get a proper unit of newtons, so that we can then make sure that our unit analysis comes out okay. Alright, just to kind of give you an example, basically just to kind of see whether or not we're in the right ballpark for charges and whatnot, I just kind of give this example of showing how to find the volume in cubic centimeters, finding the mass in kilograms after conversion, finding its weight, and then using Coulomb's law with some estimations on the distance at which the aluminum foil was picked up off the table itself. And this can be highly dependent upon the day and all that sort of stuff, so just be aware that this can vary based on environmental conditions, as I mentioned before, that you may need to do this a few times in trials and get a nice statistical average of the distance between the foil and the charged object in order to get a better estimate of the Coulomb force being applied. Here again, I wrote down the constant in Coulomb's law here. Again, we're making the assumption that we're looking at the exact moment when the force of the electrostatic charge overcomes the weight of the object, and then just using the example here, I get about 6.09 nanocoulombs, which is on about the right the order of magnitude in which charges are usually found in normal electronic devices that you might use, particularly held in capacitors that those electronic devices might use. Certainly we're not using Coulomb's levels of charges, nor are we experiencing that even when we kind of feel that static discharge, when we kind of rub our feet on the carpet and whatnot. So hopefully this helps. If you have any questions, again, don't hesitate to ask me. And just remember, be safe this 4th of July weekend. And I'll see you later this coming week.